What would happen if you slipped and fell into a planet with no place to stop? Before you hangs Neptune, a deep blue sphere resting quietly at the edge of the solar system, nearly 4.5 billion kilometers from Earth. Yet inside this planet lies some of the most violent forces ever known. The moment you touch the atmosphere, everything begins to spiral out of control. The deeper you fall, the pressure rises exponentially, exceeding Earth's atmospheric pressure by millions of times. Here, familiar physical rules begin to collapse as gases turn into liquids. Liquids transition into states of matter that have never existed on Earth's surface. If you keep falling, what will confront you with death first? Supersonic winds? Absolute cold? Or pressure that crushes every biological structure? Let us begin unraveling this deadly descent. This is not just a fall, but a journey into the limits of physics and life itself. If you were to step inside Neptune, what you would encounter would not be solid ice, but a form of matter that is alien, violent, and completely unlike anything that exists on Earth. In astronomy, the word ice is a technical term that refers to volatile compounds, primarily water, ammonia, and methane. Substances that exist as gases or liquids under Earth, like conditions, but become frozen far from the sunday. And this is where the confusion begins. Inside Neptune, there is no liquid ocean like those on Earth. There are no seas, no water-air boundary, no familiar interface of any kind. Instead, most of the planet's volume consists of a mixture of super-compressed fluids and gases in non-traditional states, where pressure and temperature are so extreme that familiar physical definitions no longer apply. Imagine a region where matter behaves partly like a liquid and partly like a gas. The outermost layer of the planet is a thick atmosphere made mostly of hydrogen and helium, similar to Jupiter and Saturn, but with one crucial difference: methane. Methane in the upper atmosphere absorbs red light from the sun and reflects blue wavelengths, creating Neptune's deep, iconic blue color. That blue is not an ocean, not ice, but an optical effect driven by atmospheric chemistry. Neptune has no solid surface. If you were to fall into Neptune, there would be no point at which you land. You would simply descend into an environment that becomes denser, hotter, and more hostile with every passing moment. Unlike Earth, where a solid surface acts as the final boundary between survival and death, Neptune has no such line. The planet is a continuous gradient, gas to compressed fluid, to supercompressed matter, to core, there is no moment of impact. There is only an irreversible transition from conditions that are uninhabitable to conditions where physical existence itself is no longer possible. And once you understand that Neptune has no surface, no stopping point, no bottom, a far more unsettling question immediately arises. What would actually happen if an object or a human began to fall into it? The moment you begin falling toward Neptune, there is no impact, no surface rushing up to meet you, no familiar endpoint waiting ahead. The only thing that exists is gravity, silent, persistent, and utterly unforgiving by the numbers. Neptune's surface gravity is about 1.14 times that of Earth. On paper, it doesn't sound terrifying. If you were somehow standing beside Neptune in imagination, you wouldn't even feel dramatically heavier. There is no immediate crushing force. There is no warning sign that you have stepped into a trap with no way out. Neptune's gravity is strong enough to hold on to anything that enters its atmosphere. Once you begin to fall, escape by inertia or simple thrust is no longer an option. Unlike rocky planets, where a solid surface provides a final stopping point, Neptune allows no such ending to exist. Only a continuous increase in acceleration and in the density of the environment around you on Earth. A fall has a clear structure: falling, acceleration, impact, and an end. Neptune is different. Here, falling does not lead to impact. Falling only leads to more falling. As you descend deeper into the atmosphere, your downward acceleration does not ease in the way intuition might expect. Gravity continues to pull you inward, while atmospheric drag is not yet strong enough to create a stable terminal velocity like falling through Earth's air. You are caught between two forces: gravity that never relents, and an environment that grows steadily denser. All of the energy of your fall is converted into heat, pressure, and mechanical stress acting directly on your body. Even the sensation of falling becomes something entirely different. On Earth, free fall briefly creates a feeling of weightlessness. On Neptune, that sensation does not last. As gas density increases, drag begins to act powerfully on your body, but not in a way that slows you to safety. Instead, it twists, compresses, and stretches you in multiple directions. You are no longer falling through empty space, but through a medium that is slowly becoming a fluid. Because there is no solid surface, Neptune completely erases the idea of a safe point on Earth. No matter the height, the ground is always a fixed reference. On Neptune, no such reference exists. And this is what makes the scenario of falling into Neptune especially horrifying on a philosophical level. You are not killed by a single mistake. You are pulled into a chain of physical processes with no choices, no escape, and no natural stopping point. The moment gravity pulls you deeper into Neptune, the first thing that truly takes hold is not pressure or heat, but the atmosphere itself. At the highest layers, where you first brush against the planet's atmosphere, temperatures range from about -214 degrees Celsius to -240 degrees Celsius. This is the cold of a place that receives almost no solar energy. At a distance of nearly 30 astronomical units, sunlight reaching Neptune is hundreds of times weaker than it is on Earth. What surrounds you is a deep, dim blue darkness. The colors seen in images are the result of scientific data processing, not human vision. Under these conditions, heat loss begins almost immediately. Thermal energy is drawn from the body faster than any biological process can compensate. Blood vessels begin to constrict, neural responses slow, and biological tissues enter a state of functional shutdown. Not because you freeze to death in the familiar sense, but because the chemistry of life no longer has enough energy to continue. As you descend further, you encounter the fastest winds ever recorded anywhere in the solar system. Measurements from Voyager 2 show wind speeds reaching 2,000 to 2,100 kilometers per hour, faster than the most powerful storms on Earth, faster than the speed of sound in dense atmospheres. And most terrifying of all, these winds are not short-lived phenomena. Neptune's superstorms can last for years, even changing shape without dissipating. For a biological body evolved on Earth, this is utterly intolerable. Layers of gas moving at different speeds and directions pull, twist, and tear the body at the tissue level. When sunlight becomes so weak that it no longer plays a biological role, the human circadian clock collapses. Neptune is often called an icy planet, yet its atmosphere is one of the most dynamic and violent environments ever observed. And as you are drawn deeper into that machine, something strange happens, something that shatters the last piece of human intuition. The temperature begins to rise. Because Neptune is not freezing, it is radiating heat, and that is where the story turns to the next paradox. Where the deeper you fall, the closer you move to fire, not ice. In the upper layers of the atmosphere, Neptune truly is one of the coldest places ever measured in the solar system, with temperatures plunging to between -214 degrees Celsius and -240 degrees Celsius. But descend just a little deeper, and something unusual appears. the temperature begins to rise. In Neptune's thermosphere, measurements show that temperatures can reach around 477 degrees Celsius. So where does the heat come from? The answer lies in Neptune's physical nature itself. This planet emits about 2.6 times more internal energy than it receives from the Sun. It is an active system releasing heat. The first mechanism is compression heating as you fall deeper. Pressure increases continuously. Gas molecules are forced closer together. They move faster and they collide more frequently. The second mechanism comes from heat escaping the planet's interior. Neptune still retains a large amount of heat from its original formation more than 4.5 billion years ago. In addition, radioactive decay within its rocky core continues to supply energy. This heat does not escape gently. It is trapped, accumulated, and then released through massive convection currents. And this is where the third mechanism appears: atmospheric gravity waves. These waves carry energy from deeper layers upward, heating the thermosphere far beyond what sunlight alone could produce. The result is a completely inverted thermal structure: cold above, hot below. Earth-based biology, accustomed to stable temperature gradients, has no way to adapt. As you continue to fall deeper, temperature is no longer an abstract number. It becomes an active force of destruction. But heat is still not the worst thing waiting ahead. Because as pressure rises and temperatures continue to climb, the matter around you begins to change state. And that is the moment you enter a world even stranger than heat or cold. Layers of clouds where life cannot exist, where matter is constantly shifting phases, and where no stable environment can endure. At the highest levels, methane clouds dominate. On Earth, methane is a gas. On Neptune, under its unique temperature and pressure conditions, it condenses into fine cloud particles. This layer is what gives the planet its iconic deep blue color. But that beauty hides a harsh truth. This environment is extremely unstable. Methane cloud particles are swept along by ultra-fast winds, constantly colliding, dispersing, and reforming in relentless convective cycles. Deeper down, ammonia clouds emerge in the mid-atmosphere. On Earth, ammonia is already a highly corrosive substance. On Neptune, it exists in a strange regime where temperature rises, but pressure increases even faster. Cloud droplets are no longer liquid in the familiar sense, but continuously shifting mixtures of compressed gas, supercompressed fluid, and unstable molecular clusters. Then come the water clouds, a concept that sounds comforting, but is actually the most dangerous linguistic trap of all. These are not water clouds like those on Earth. On Neptune, water clouds form under extreme pressures, where water is no longer benign H2O. The critical factor lies at the boundaries between these layers. Neptune has no gentle transitions, temperature, pressure, and chemical composition change abruptly with altitude. For Earth-based biology, which depends on environmental stability to maintain protein structures and cell membranes, this is an immediate death sentence. Within these cloud layers, nothing remains still. Cloud particles are constantly falling, rising, breaking apart, and reforming. Any object is forced to participate in an endless cycle of phase transitions. These cloud layers also raise a profound question for the search for extraterrestrial life. If even water, the symbol of life, can become hostile under different conditions, how cautious must we be when extrapolating from Earth to the wider universe? And then, as you are pulled through the supercompressed water cloud layer, one parameter begins to dominate everything else: pressure. On Earth, atmospheric pressure is about 1 bar. At the deepest point of the ocean, that number rises to roughly 1,000 bar. Already enough to crush a submarine if it is not specially designed. On Neptune, pressure does not increase linearly. It rises exponentially as you are pulled deeper into this surfaceless planet. As you move closer to the deeper layers, physical models indicate that pressure can reach tens of thousands of times Earth's atmospheric pressure, estimated at nearly 50,000 bar near the Mantle. The first consequence is total lung collapse. Not because of oxygen deprivation, the oxygen problem ended long before, but because there is no longer any space for gas to exist. Next comes the circulatory system. Blood, though a liquid, no longer flows in any familiar way. Extreme pressure alters its viscosity and even the way molecules interact with one another. The heart, if it is still functioning, cannot generate a sufficient pressure difference to pump blood. Biological circulation collapses not because the heart is weak, but because physics no longer allows motion. What is striking is that Neptune does not need to kill through sudden force. Pressure does not attack. It compresses gradually, continuously, irreversibly. There is no explosion. There is no clear breaking point. There is only the steady reduction of the space in which existence is possible, until there is nothing left to compress. These pressure levels, the familiar states of matter on Earth, solid, liquid, gas, no longer fully apply. As pressure continues to rise, the material around you enters an even stranger regime, where water, ammonia, and methane are no longer substances in the usual sense, but become super-compressed oceans with phenomena never observed on Earth. And it is there, deep beneath unimaginable pressure, that one of the most bizarre ideas science has ever proposed about Neptune may exist, a place where diamonds could fall like rain. If pressure marks the final boundary of biology, then Neptune's hot ice mantle is where that boundary no longer has meaning. Neptune's mantle is believed to be composed primarily of water, ammonia, and methane. Under immense pressure and temperature, these substances do not freeze. They are forced into supercompressed and supercritical phases, where the boundary between solid, liquid, and gas breaks down. In this environment, water is no longer a solvent for life. What makes this mantle famous and profoundly strange is the phenomenon known as diamond rain. Under pressures of tens of thousands of bar and temperatures of thousands of degrees, methane molecules are torn apart. Carbon does not evaporate, it crystallizes. High-energy laser experiments in laboratories have confirmed that when methane-rich mixtures are compressed to Neptune-like conditions, nanodiamonds form and fall downward. Pause for a moment to grasp how alien this picture is. On Earth, diamonds are the product of time and pressure deep within rocky mantles. On Neptune, diamonds are rain, particles of matter caught in planetary flow, falling, accumulating, and potentially dissolving again in deeper layers. The hot ice mantle also acts as an energy engine for the planet, helping sustain the extreme weather above and directly linking to Neptune's unusual magnetic field. Everything here changes with pressure and temperature far beyond the capacity for self-organization of any living system we know. Yet this mantle raises a deeper question for planetary science. If supercompressed oceans can exist not to support life, but to shape entire worlds, how many planets out there are we misunderstanding because we speak in Earth-based language? Neptune forces us to separate two ideas we often conflate: the presence of compounds and the capacity for life. As we descend further, diamond rain is no longer the only defining feature. The supercompressed mixture grows denser, more electrically conductive, and more efficient at transmitting force. So, what keeps Neptune warm, active, and stable over billions of years? The answer lies in its rocky core, a heart we cannot touch, yet one that determines the fate of the entire planet. Modern planetary models suggest that Neptune's core is a dense rock metal mass buried deep beneath its supercompressed mantle, with an estimated size roughly comparable to Earth. However, rock here does not carry its familiar geological meaning. Under pressures of tens of millions of bar and temperatures that may exceed 5,000 to 7,000 K, matter no longer clearly distinguishes between solid and liquid. We have never directly observed Neptune's core. Everything we know comes from gravity measurements, moments of inertia, magnetic fields, and the heat flowing outward. Yet from this indirect evidence, a consistent picture emerges. Neptune's core is still hot, and it is this heat that powers the entire planetary machine above it. Neptune emits internal heat at roughly 2.6 times the amount of energy it receives from the Sunday. Two main mechanisms are widely accepted: residual heat from its formation and radioactive decay of heavy elements within the rocky core. The crucial point is this: Neptune never fully cooled. Contrary to older assumptions that ice giants would freeze to death quickly, Neptune's core reveals a different reality. With sufficient size and the right internal structure, a planet can sustain internal activity for extraordinarily long periods, even at the far edge of the solar system. This heat flow from the core drives convection in the mantle, indirectly producing the phenomena we observe above: supersonic winds, storms that persist for decades, and most notably, an anomalous magnetic field. Another key detail emerges: Neptune's core does not sit at the center of its magnetic field. Data from Voyager 2 show that Neptune's magnetic field is strongly offset and highly tilted relative to the planet's rotation axis. This implies that the dynamo region, where electrically conductive material is in motion, does not coincide with a classic central core, but may instead lie near the boundary between the core and the supercompressed mantle. The core does not directly create the magnetic field, but it determines the structure of the region that does. And as energy continues to rise from that hidden heart, interacting with conductive matter and warping invisible magnetic lines around the planet, displaced magnetic fields and lethal auroras emerge. What we know begins in 1989, when Voyager 2 flew past Neptune and revealed a magnetic axis tilted by about 47 degrees relative to the planet's rotation axis and displaced more than 0.55 planetary radii from its center. The entire magnetic system is pushed off balance, as if it were generated by a planet that is internally unstable. This leads to an immediate consequence. The magnetic poles do not lie near the geographic poles on Earth, Auroras are concentrated around two relatively fixed regions. On Neptune, auroral zones wander and distort, shifting with the planet's 1/6-hour rotation. On Earth, a dense atmosphere and a stable magnetic field help dissipate this energy. On Neptune, everything unfolds with greater intensity, deeper penetration, and far more violence. Models show that Neptune's surface magnetic field strength is comparable to, or even stronger than Earth's, but its asymmetric structure causes radiation belts to be unevenly distributed. More disturbing still is that Neptune's magnetic field is not stable over time. This instability gives rise to unpredictable magnetic storms, bursts of energy that can erupt without the kind of advance warning Earth receives from solar activity. When the solar wind interacts with this off-center magnetic field, it forms a long, twisted magnetotail that is constantly stretched, bent, and compressed. The space surrounding the planet becomes a zone of electromagnetic turbulence, hostile to any device, any body, any biological system. For humans, auroral radiation does not need to strike directly to be lethal. Simply being within its influence can disrupt the nervous system, scramble electrical signals in the brain, and desynchronize biological reflexes. This is a form of danger without obvious pain. No burning, no freezing, just the silent disconnection of life itself. Neptune's magnetic field forces planetary science to confront a deeper question. Is a magnetic field always a prerequisite for life? On Earth, the answer is yes, but Neptune reveals the opposite possibility, that a strong magnetic field, when structurally distorted, can become not a shield, but an instrument of destruction. The journey of falling into Neptune is not an instant death, but a sequential and brutal collapse of the human body as it confronts the extreme limits of the universe. In the highest cloud layers, supersonic winds far beyond any scale experienced on Earth tear apart the mechanical bonds of equipment and biological structures alike. As the descent continues into the thickening haze, sub-zero cold paralyzes molecular motion itself, until at last the planet's immense core pressure delivers the final act of erasure, crushing every remaining boundary of matter into atomic dust. Here, the line between life and death is erased by the primordial force of an ice giant, a realm where the laws of physics operate with absolute precision and emotional indifference. The suffocating hostility of Neptune is not merely a problem of survival. It is a reminder of humanity's small place on the cosmic map. If a planet within our own reach already contains such a terrifying physical hell, then the icy worlds beyond our solar system, larger, denser, and more alien, may conceal phenomena that surpass both imagination and conventional logic. As this descent into nothingness comes to an end, the real question is no longer whether humanity could ever conquer such worlds, but how many places exist in the deep darkness of the universe where conditions are so extreme that life never had a single chance to begin. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.